Good morning, students. Today we will discuss about the concept of syntax-directed translation. The outline of this today's class is what do you mean by syntax-directed translation. So that one we will call it as an SDD charter. Then after that we will discuss about syntax tree. Then after that how to construct a syntax tree. Then syntax tree for S attributed definition and problems on that syntax tree for S attributed definition. So this is the outline of this today's class. So first we will discuss about syntax directed translation. So in previous class we have discussed about syntax directed definition. Okay, so today we will discuss about syntax directed translation. This we will call it as SDT. SDT, SDT. So in short term we will call it as SDT. So this syntax directed translation is a context-free grammar with embedded semantic action. Yeah, so this one we will call it as an STD. So it is a context-free grammar with embedded semantic rules. Semantic actions is nothing but we will have in the STD in a syntax directed definitions we have derived a n number of semantic rules for a given problem or for a given grammar. So here this is embedded with context-free, embedded with syntax semantic actions in the context-free grammar. Okay, these semantic actions are nothing but the sequence of steps or program fragments that will be carried out when the productions is used in the derivation. So these semantic actions are nothing but a sequence of steps or a program fragments, what we are calling. Okay, so this sequence of steps will be created when you are deriving the productions. Okay, so when you are deriving a particular string, so at that time we are using a number of productions. At that time we are using these semantic actions. Okay, so the sequence of steps. So we have derived a number of past trees. So for the given we are derived left derivation, right derivation. So all those things we have discussed in this second module. Sorry, in third module we have discussed all those things. Okay, so here, so when you're deriving a particular string, so we will have a number of steps. We have sequence of steps. Those steps we will call it as a semantic action. Okay, so this SDT are used for to build a syntax tree for the programming construct. Okay, so syntax tree. So we have derived the parse tree. So now we'll have a syntax tree. We will discuss that what do you mean by syntax tree. So this is nothing but an abstract of that parse tree. We'll call it as the syntax tree. We'll come to that. Okay, so then it will, when you translate the infix expression to postfix expression, so at that time so that is infix to for infix expressions to postfix notations. So at that time we are using this SDD, and to evaluate the expressions at that time we are using the syntax directed translation. Okay, now what we call it as a syntax tree. Okay, syntax tree are also called abstract syntax tree, is a compressed form of parse tree. Okay, so compressed. So here when you are compressing, what happens? So that the meaning should be same, but it contains only important things. Okay, so that one we will call it as a syntax tree is called as abstract syntax tree, is a compressed form of parse tree, so which is used to represent a language construct. So suppose when you want to derive a particular string, so we will construct a parse tree using derivations. After that, what we are doing, so only important thing we are taking, that we are representing, that one we will call it as a syntax tree or an abstract syntax tree. So in syntax tree for an expression, for a particular given expression, each interior node represents an operator. Okay, so each interior nodes, it should represent only operator, and children nodes. Okay, so children node represents the operands. Okay, so in syntax tree what we have, so in root we will have it may be operator or it may be operand also. Okay, we may have operand also. So at that time what we are doing, so here when you come to the syntax tree, only the interior nodes will be an operators and leaf nodes will be a operands. Okay, so in any general programming construct can be handled by making up an operator for the construct and treat semantically meaningful components of that construct as an operand. So you can, in any programming construct, okay, so can be handled by making up an operate for the constraint. The operator for the constraint means it may becomes a root of the interior nodes, or it may be a root, and left and right childs we will have an operands. That one we call the construct as an operand. Okay, so usually a root will be operator and leaves will be a operands. So that one we will call it as a abstract syntax tree, or a simply we will call it as a syntax tree. So we will take an example. See here, this is a 6 plus 4 minus 2. Okay, so this is an expression. Okay, so this expression will be represented in the abstract syntax tree. Okay, so I already told that the root will be operators. Okay, so here, so 6 plus 4, so 6, and this is the root. Okay, so that is this is the interior node plus. Okay, so here left child will be 6 and right child will be 4. So after evaluating this, then we will have a main root, that is minus, and the right child will be a 2. Okay, so observe this following points. Okay, the operator minus represents the root node. Okay, the operator minus represents the root node. Okay, so operator minus represents the root node, and the subtree of the root represents the expression 6 plus 4. Okay, the subtree, this is the subtree, so it represents the subtree for this past. Okay, 6 plus, that is 6 plus 4. And similarly, the expression plus is the root, and 6 and 4 are the operands representing the children. So here this plus is the root, and 6, 4 are the a child of that root. So here minus is the root, and so here left subtree will be the plus 6, 4, and right subtree will be right subtree will be the 2. Okay, so it is very easy to construct the syntax tree with the help of syntax directed definitions. The syntax tree resembles the parse tree to some extent, but with the following changes. This is the difference. So what difference? So in syntax tree, see here, in syntax tree, all operands and keywords appear in the interior nodes. Okay, so in syntax tree, all operators will becomes in interior nodes only, interior nodes. Okay, so in parse tree, all operator and keywords are appear as a leaf node. Okay, so here that is the difference. So in parse tree, all operators and keywords appear as a leaf node, but in syntax tree, those operators and keywords are appeared as an interior nodes. That is the difference between a syntax tree and the parse tree. It is very easy to construct. Okay, so this is an example. So for the given following grammar shows the parse tree and syntax tree for the expression 3 star 5 plus 4. So this is an grammar what we have. So using that grammar, we are deriving a parse tree. Okay, so then after that, equivalent syntax tree. So here first one is 3 star 5. So that is in this productions we have E tends to E plus T. Okay, so we have productions E tends to E plus T. So this productions we will take first. Okay, sorry, this productions we will take first. Okay, so E tends to E plus T. So this one E tends to E derives E plus T. Okay, so E tends to see here operator is leaf node here in this parse tree. So then after that what we have? Okay, so then we have E tends to T we have. Okay, so E tends to T. Okay, we have E tends to T. So then here we need to 3 star 5. So that is 3 star 5 is T tends to T star F. So here T tends to T star F. We are representing that one as a T1 because of left derivation. Okay, so here we have a left recursion is there. So for that we are writing a T1 and T1 star F. T1 star F. That is the yield of the tree will be the T1 star F. This is intermediate yield. Okay, so T star F. So then after that T tends to F. Okay, so T tends to F. Here T tends to F. Then after that F tends to digit. Okay, so T tends to F and F tends to digit we have, and here F tends to digit we have, and T tends to F and F tends to digit. So this is the yield of the final tree. Okay, so that is 3 star 5. Okay, plus 4. This is the yield of the parse tree. that is 3 star 5 plus 4. So this is the derivation of the past using the given grammar. So then how will the same thing will be represented using syntax tree. So this is the abstraction of the syntax tree. Sorry, abstraction of the past tree. So here what we are doing, so here this is the yield of yield, we are taking only yield. So here 3 star 5. So here this is the 3 left child and 5 will be the right child and star will be the root of that particular child. 3 star 5. So then this is the left child. So then right child we so for this one 4 will becomes the right child of that syntax tree, and this plus becomes the root. Okay, so this plus becomes the root, and the right child will be the 4 and left child will be the 3 star 5. See here, so how many non-terminals, all those things are coming. So here in syntax tree we don't have any terminal at all. Sorry, non-terminals. We are directly we have values and operators. Okay, so that one we will call it as a syntax tree. So that is syntax tree is nothing but an abstraction of the parse tree. So here this is the abstraction of the parse tree. Okay, so this one we will call it as a syntax tree. So for that, to develop this parse tree we are using that STD. Okay. Then how we will construct the syntax? That is one a general example. Then how we will construct the syntax tree? Okay. So here the syntax tree for an expression can be constructed using two STDs. Okay. So that STD is nothing but a syntax direct definitions. So we already know that there are two types of attributes: S attributes and L attribute. Okay, S attribute definition and L attribute definition, same thing. So here the S attribute definitions, which is used for bottom-up parsing. Okay, to construct a syntax tree, so from bottom to top, if you are developing that, at that time you are using this S attribute definition. So when you are using top-down approach, at that time we are using L attribute definition. So using these two things, we will construct a syntax tree. So first we will discuss about the S attribute definition construction of syntax tree. Okay, so here first one is a syntax tree for S attributed definition. We are concentrating on S attribute syntax tree. So then after that completion of this, we will move on to L attribute syntax tree. Okay, so here S attribute definition, that is nothing but it is a synthesized attributes we have. Synthesized attribute means we are deriving the tree from bottom up. Okay, so that is we are deriving the values of root by the child. So each node in a syntax tree represents a programming construct. Okay, so each node in a syntax tree, it will represent a programming construct, and the children of the node represents the meaningful of the construct. Okay, so we all know that. So syntax tree, it will represent a programming construct, and children of the node represents the meaningful component of the construct. So this is the example, this is the construct. Okay, so plus is the root is the construct, and these two left and right nodes are the children nodes. It should have a meaningful component of construct. So here we have an operand E1 and E. So these are the meaningful construct for the plus. So using, when you add those two, to add this E1 and E2, so we need this root. Okay, so that is a syntax tree node representing an expression E1 plus E2 as label plus, and two children representing the sub expression E1 and E2. So here when you have this expression, so for that if you are constructing a tree, so simple tree, so that is E1 and E2 becomes a child of the tree, and plus becomes a root of the tree. Okay, so it means we are deriving from the bottom up approach. Okay, so here when you are constructing creating a syntax tree, for that here we have two useful functions we have. Okay, so one is a leaf node, another one is intermediate node. Okay, so here interior nodes are a root node for the particular child nodes. Okay, so we have two nodes in a tree. So one is a leaf node, another one is interior nodes. Okay, what do you mean by leaf? What is the function of leaf node? So here we will have leaf. Okay, so the parameters are OP and val. What is OP? So this Okay, so this function is called only for the terminals, and it is used to create a only leaf node. Okay, so here leaf, these functions leaf parameters are op and val. So these functions is called only for terminals. Okay, so this function is called only for terminals, and it is used to create a leaf node only. Okay, so op is nothing but a holds the label of that particular node, intermediate node, and val field holds the lexical value obtained from the lexical analyzer. So what values we have to, obtained from the lexical analyzer to represent that value from the lexical analyzer, we will use that VAN. Okay, so this leaf OP, that is nothing but an operator. Okay, so OP field, that is nothing but a label. Okay, so field holds the label for the node. Okay, and val is represents the value of that. Okay, so another one is node. Okay, so next function, so it will be node OP comma C1 C2 C3. Okay, so this functions is used to create only interior nodes. Okay, so here what is this? OP fields holds the label for that node. The label is nothing but a name for that node, and is this C1 C2 are nothing but a pointer. So interior nodes, what happens? It should label we have, and it should points to the leaf node. Okay, so for that we need pointer. So children for the node labeled as OP. Okay, so here, so OP is nothing but a label, and C1 C2 are the pointers for interior nodes, and another one is leaf functions, that is OP is nothing but a label, another one is val is nothing but a value derived from the lexical analyzer. Okay, so these are the two functions we are using to construct a syntax tree using S attributed definition. We will take one example. So first we need to obtain the semantic rules to construct a syntax tree for the simple arithmetic expression using bottom-up approach. Okay, so first what we need to do, so we need to derive some semantic rules. Okay, so that is nothing but an SDD. So we need to derive the semantic rules. After deriving that, we will construct a syntax tree. So here this is the grammar they have given. So for simple arithmetic expressions, e tends to e plus t or e minus t or t, and t tends to t star f or t slash t division f or f, and f tends to e or tends to digit or id. So it is easy to construct a syntax tree with the help of SDD. So that is nothing but with the help of that syntax directed definition, that is nothing but we need to generate a semantic rule. So with using those functions. Okay, so first take addition. So e tends to, we will have e1 plus e2. Okay, so why you are taking e1 plus e2? So here we need to remove the derivation, left recursion we need to remove that one. So here we will take that for the production e tends to e1 plus e2. So we have to use a rule that creates a node with plus. Okay, so we have to create a node plus for OP field. Two children are e1 dot node and e2 dot node. So two children, that is here we have a productions e tends to e1 plus e2. So what we are doing, this is e1 dot node, we are making that. Okay, so e1 dot node, and this one will be the e2 dot node. Okay, so here we are creating a new node. So this one I have told now. So this is new node. Okay, so we need to create new node with these functions. Okay, so here, so what we have, so this is we have, so e1 tends to and, so here, so we are creating a new node. Okay, so here what is the operator? That is nothing but a plus. Plus is the operator. Okay, so e dot node is equal to, so we are creating a new node. E dot node is equal to new node. The parameters will be a plus, OP, and these are the nodes, e1 dot node comma e2 dot node. For the productions, e tends to e1 plus e2. So just we are creating a new node, and after that what operator we have, that one comma, so that particular non-terminal if it is e1 is there, e1 dot node comma e2 dot node, and here e tends to, that is e dot node. Okay, so left side e dot node is equal to, so we are creating a, for this e dot node we are creating a new node, that is new node is equal new node, that is parameter will be the plus comma, that is this is the arithmetic operator, that is plus, and e1 dot node comma e2 dot node. This is the semantic rule for a, okay. So using new operator we are creating this function node, okay. So like that we are creating a new node using a new operator. So like that create all the new nodes for productions, okay. So here for a same example like that we are creating all the new nodes. That is nothing but a semantic rule for each productions. E tends to e1 plus t. So here e dot node is equal to a new node, that is here plus is there, plus, and e1 dot node plus t dot comma e2 dot node. So like that e tends to e1 minus t is there. So that is e1 minus e2. So that is, okay. So e dot node is equal to new node, and here minus is there, minus comma, so e1 dot node comma t dot node. So like that t tends to t1 star f, that is t dot node is equal to new node. So here star is there, make a star as a parameter, comma t1 dot node comma f dot node. So like that t slash t1 star t tends to t1 slash f. So here that is new t dot node is equal to new node, that operator, arithmetic operator, comma t1 dot node comma f dot node. So like that we are creating a new node for each productions. Like that we have last productions. So if we have e tends to t is there, t tends to f is there, f tends to e. So here same thing. So here for the productions of the form e tends to t or t tends to t is no need to, no new node is created, because since e dot node is same as that of t dot node, so the semantic rule of the productions can be written as just we are copying that, just we are creating that, we are not creating a new node, just both are same, okay. So no need to create a new node, just e dot node is equal to t dot node, and t dot node is equal to f dot node, and f dot node is equal to e dot node. So we are not creating a new node because we are not adding, or we are not doing anything, just we are same thing, it is derived from left side to right side, okay. So then we have, in addition to that, we have two more, last one, f dot digit and f dot id, okay. So here for a production form a tends to capital A tends to a, so where a is a terminal, okay. So where a is a terminal, and so if it is a is a terminal, then use the function leaf, okay. So because a is a terminal, so that's why we are using the function use. We have two functions now, that leaf. So leaf is nothing but a, so when you have a terminal, so at that time we will use this leaf function with a and a dot entry as the parameter if a is, and identifier are a val as a parameter if a number is digit. So what we are doing, so if you have f, if f is digit, so what we are doing, so we are creating a new leaf with digit and digit value. If f is tends to id, so then we are creating a new leaf with id comma id dot entry, okay. So this id dot entry will be, it points to the next node, that it points to the next value, that id particular id value. Suppose is small a value, what is it, will be 5 or a 4, so it will be, that entry will be doing here, okay. Suppose if it is digit, that directly digit value you can make it as a leaf, okay. So these are the semantic rules for the given arithmetic expression. So now we will create the we will so this is whatever we have discussed, all those things we have listed here. So all, for all the productions we will have a semantic rules, okay. So from e tends to e1 plus t2, f tends to id. So same thing we have discussed now. So we have listed all the so for simple arithmetic expression, so we have written all the semantic rules, okay. So now we will create one, we will take one example and we will create one syntax tree for the given expression. So here we have a given expression a minus 4 plus c. So a is nothing but a terminal, and this is 4 is nothing but a digits, and minus plus are the operators. Okay, so how we will create? Okay, so here consider the arithmetic expression a minus 4 plus c. So here we make use of following functions to create the node of the syntax tree for the expression with binary. So here we will have the three functions we have. One is a node, that is here we have an OP operator and left child and right child. So we will create an operator node with a label OP. Okay, so we are creating a operator. So because we are using minus and plus, so we are having operators. We are creating a operator node with label OP and two fields containing pointers left and right side. Okay, so two pointers. The first node we will create. Okay, so that is operator, that is left subtree and right subtree. So operator, that label will make it as a OP, and the two pointers contain left and right subtree. Okay, so this is intermediate node. So then this leaf node. So leaf node, if it is digit, sorry, if it is ID, so create an identifier node. Okay, create an identifier node. Okay, so that is the terminal. Okay, if it is small a, small b, so this is for small a. Okay, so if it is create an identifier with label ID, name is ID, and field containing a entry, that is nothing but a pointer. So here that a value, whatever it may be, we don't know. So that value is available in symbol table. So it points to the symbol table entry for that particular identifier. So like that, another one is digit. So that is also a leaf node. Okay, so digit we already know the value. So that is a 4 is this 4 is a digit. Okay, so, and we will for that, if it is digit is there, create a number node with label digit. The we need to name it as a digit, and the field contain the value, the digit value. Okay, so like that, it represents the value of a number. Okay, so like that we need to create a intermediate node and leaf nodes. Leaf nodes with the, it may be up, one is ID or another one is so another one is be a digit. Okay, so and intermediate node. So for that this is an example, a minus 4 plus c. Okay, so first step. So what is the first one we have? So here first we have a. So for that we need to create a one node. So this is a will be, so we already know that in abstract syntax tree. So operators are the roots, and IDs and terminals, that is digit and IDs are comes under child nodes. Okay, that is nothing but a leaf node. Here we will create a leaf node. I create a leaf node for an identifier A using the function leaf. Okay, so A is nothing but an identifier. So for that we already discussed the function. Okay, so here we are labeling that one as a P1. Okay, so new leaf. Okay, so new leaf, we are creating a new leaf with the ID and ID entry. Okay, so this one, so this is ID and entry. So this it create an identifier with label ID and a field containing entry. Okay, so entry is pointer. Okay, so here we are created a one. We are giving name as P1, and here we have a for this node we will have an ID, and another one is a entry for the particular value of a value in the symbol table. Okay, so then okay fine. So then after that what we do, we need to create a new node, new leaf node, that is 4. So the 4 is digit. So using that function, so we are that P2 is nothing but a new leaf. Okay, so digit and digit value. Okay, so new leaf digit and value is 4. So here digit 4. This is the P2. Okay. So we have created. Then we need to create an intermediate node minus. Okay. So here by creating an interior node, okay, by passing minus, okay, as the first argument and point us to the first two leaves P1 and P2 with the help of function node. Okay, so here what we are doing, so we are creating a third node, that is P3. Okay, so we are creating a third node P3. So here this is the intermediate node we are creating. So in that we are creating a new node P minus. This is the minus operator, and here P1 and P2 are the uh, pointers to the next node. Okay, so here we are created a P3, this is the minus. Okay, so and here these are the pointer, it points to P1 and it points to P2. So that is P2 is nothing but an P1 is nothing but an ID, and P2 is nothing but a digit value 4. So ID is nothing but it enters to a. So it means we have created this one a minus 4. Now we need to create this plus c. Okay, so here we need to for that we need to create a one more leaf node with id. Okay, so create a leaf node for identifier c using the function leaf. Okay, so that is the fourth node will be the a new leaf, that is id comma id dot entry, that is it labeled as id, and that pointers to the symbol table. So that C value is available in symbol table. So it points to symbol table. So enter it for C. Okay, we have created P4. Then we have created C. Now we need to create intermediate node plus. Okay, in fifth step, we are creating an interior node by passing plus as the first argument and pointers left and right. Okay, so pointers to left and left subtree identified, it will be P3, and pointers to the right subtree, that one will be the P4. Okay, with the help function node. Okay, and P5 P5 new node will be plus, and it points to P3 and it points to P4. So we have created plus, so this pointer will point to P3 and this points to P4. Okay, so now we have created a syntax tree. So with the plus, okay, so this the plus points to minus. Okay, so minus will points to id, id points to is nothing but a, and p2 points to p3 points to p2, that is digit, that value will be a 4. And here p5 points to right side, that one will be the id, that id points to entry for c. So this is a syntax tree we have created for the given function. Sorry, given string, that is a plus, that is a minus 4 plus c. Okay, so here same thing we are the past and annotated past depicted the construction of a syntax tree for the arithmetic expression. How it will looks like. See here, annotated past and this that is past and this syntax tree. See here. So this plus. So what we are using that productions e tends to e plus t. Okay, so e tends to e plus t, that is e dot node derives e node plus t node. Okay, so this plus is depicting here. Okay, and e node plus is depicting here now. So then this t dot node, it tends to id. Okay, so this t dot nodes will comes to here. Okay, so then this e dot node will derive e dot node minus t node. So this is the minus now. So this minus e node will becomes to here. Okay, so and this t node is nothing but a digit. So this comes to mapping with this. Okay, and this e tends to t, then t tends to id. So this is mapping to here. Okay, same thing. So we are but the syntax tree is nothing but an abstract. So we may get a number of nodes, more nodes in this past tree, but here when you are deriving that syntax tree, it is be an abstract of that past tree. Okay, so like that we will construct a syntax tree for the given string. Okay, so here if you create using that functions, okay, so this is enough. Use these functions for leaf node and intermediate node, and create this one, that is enough. If they ask the question, create a syntax tree for the given string. Okay, so use these functions and write that syntax tree. Okay, so this is no need, just for your understanding we have done this one. Okay, so we have discussed today. We have discussed about what do we mean by syntax directed translation. So then after that, uh, construction of a syntax tree. So then after that, a syntax tree for S attributed definition we have discussed, and we have discussed one problem on